Hello again, everybody. This is Dr. Peterson for Stratigraphy, Geology 311 at UW Oshkosh, Spring 2021, Week 5. This week, we are going to be covering the horizontal dimension. So this is Chapter 6 in the Brookfield text. And in this lecture, we will be talking about principles of physical correlation, lateral changes in the stratigraphic record, and a little bit at the very end about some mapping philosophy. So let's jump right in. Last week for Chapter 5, we looked at the vertical dimension in the Brookfield text, where we looked at how units can vary in grade vertically. This week, we're going to be touching back on some of that because you can't really completely separate these two concepts, but what we're going to be focusing more on how units change in the horizontal direction, and this means they have to be traced from some distance from one to the other, and this is where correlation comes in. Now, there's two ways of correlating. You can correlate in space, which is what we're going to be doing or talking about more in this lecture, and you can correlate based on time, which is something we'll talk a little bit more about next week. And it's also very important that we discuss some differences between correlating with precision and correlating with accuracy. And there's a figure in your textbook, 6.1, that I actually think is kind of clever. They're using a bullseye pattern as an example of what we mean by precision versus accurate. You can have high accuracy, such as all of the little X's on the target, but low precision. They're kind of scattered all over the place. Or you can have high precision and low accuracy, where you're not hitting the target at all. You're not accurate, but you are very precise in your grouping. You can have high resolution, where you can differentiate between your two marks, and low resolution, where they're kind of all over the place, intermingling. So thinking about this in terms of lateral or horizontal stratigraphy, we look at the differences between precision and accuracy, and scale, of course, being an important factor. But for example, you can have very precise space correlations, where you'd correlate low-angle beach cross-bedding within a sandstone body, and you can get very precise in how those individual crossbeds vary throughout the lateral unit. Or you can have more of an imprecise space correlation, looking at an interbedded limestone with shale units, and you can trace this large body of rock from one place to another, but the individual beds may not. So it's important just to kind of keep this diagram maybe for future reference in any field of research that you may get into. Precision and accuracy are not the same thing, but both are very important. When we start looking at physical correlation, it brings up once again Steno's principles of superposition and cross-cutting relationships, horizontality and continuity, which are still very important concepts and still very useful, but they're particularly useful more in the local section and description. When you're talking about tracing over large distances, things can get a little bit more complicated. So here in figure 6.5, you're looking at part of the Cambrian rock section of the Grand Canyon. So you're looking at the parts around Arizona. And simple lithologic correlation, and this of course is going to be based on exposures that you have access to and direct field observation. But what I want to point out here is we're looking at 9 different sections over hundreds and hundreds of kilometers correlating across. Now, there's some other discussion in this chapter that I recommend reading, where it's talking about the dotted lines down there by the Bright Angel Shale and the sandstone unit. The dotted lines are actually based on fossils, which means that that is a time correlation. But what I just want to point out is how the lithologic correlation does not match up with that, and that's an important observation to make. But the principles that Steno proposed are still useful, but we have to kind of take them with a little bit of understanding that there are going to be more complications when you start looking at things in a much larger field observation. We can also correlate units based on seismic cross-sections, and I have to stress this very strongly, these are not outcrops. I mean, it looks kind of like an outcrop. It looks like a black and white image of various units that have been distorted. Instead, what you're actually looking at is the reflection of rocks based on some kind of acoustic or seismic disturbance, and the travel time. So you notice the 1 second, 2 second, 3 second, and so on. Now, some of the features on this diagram are a little hard to see, so I'm going to highlight them for you. So there's a B here, there's an H, another B, F, E, A, G, there's another A, and D. So when we look at this, our main reflector surface, as we call it, is A. And this is your water depth reflector. So that's kind of the difference between water and when we actually start seeing a reflection of vibration or energy off of rock itself. Oh, and I did apparently miss C here. And C is important because what C is telling us is we have this kind of disturbance of the original fabric of the sediment in some way here. So whatever's down there is behaving differently than the materials around it. And if you look carefully now, you can start seeing other kind of seismic reflectors, even though some of these are obliterated a little bit. We have some packages that we can trace as well. So we'll be coming coming back to this more in upcoming weeks, but I just want to use this as an opportunity to kind of point out that what looks like rock is not, but we can still use the patterns that we see in this form of seismic section. We can also then use that for correlation with other seismic sections, and then later calibrate what kind of rocks these actually represent. So how do we even get these seismic reflectors in the first place? How do we get these seismic sections? Well, the methods are fairly similar depending on where you are, but there are a couple of differences whether you're doing it over water or doing it on land. On land, sounds are somehow produced either with a shot pellet, or they'll have large weights that'll slam on the ground, or sometimes setting off explosives. With our nautical or seismic sections over oceans, they use air guns. So you'll have a ship and it trawling behind it on a large cable. You've got some kind of an acoustic or sonar source, and that bounces down through the water, and it bounces off the different layers, and it penetrates at different depths depending on the frequency. And then it bounces back up, and it's picked up by these underwater phones that are being held behind. And these are detecting how long it takes to get that signal back. And different sediment types, whether it's hard rock or muds or clays or sands, are going to bounce that back different. Also, depending on how the fabric of that rock is stacked, it can also affect how it comes back. When we were talking in the previous diagram of how some of those reflectors have been obliterated, that doesn't necessarily mean that in every case that the rock units themselves are distorted. It can be distorted from the next round of seismic data collection. So seismic units are really, really important because that's how we can understand what's going on in the subsurface in many, many cases, but it does require a considerable amount of calibration. So here's just a couple examples of some of the ways that we can do terrestrial or continental seismic collection. On the far left, you've got what we kind of nickname a Thumper System. So there's this large weight and a big heavy plate you put on the ground, and that little, six-wheeler has this big piston on the back, and it raises up a weight and it slams it down on top of that. Meanwhile, your receiver phones are scattered around the area. On a smaller scale, if you're trying to just get with some of the more local, or not local, but the more superficial units, you can just use a sledgehammer and a large plate and then the phone array around it. And if you want to go really deep, yeah, you can use explosives like dynamite or a shotgun pellet, shooting it into the ground and waiting for the seismic signal. But I want to stress that this isn't like the beginning of the first Jurassic Park film where they're using seismic methods to get pictures of fossils in the ground. It doesn't work like that. You don't get an X-ray. You get a printout, or you get an image of where there are differences in the physical properties of the subsurface materials. So if there is something down there that has a specific shape, you're not going to see that shape. You just see that it behaves differently when it's met with these acoustic and seismic waves than the surrounding materials. At its very basics, seismic methods work because our vibrational or seismic waves will travel through different types of rock at different speeds, and this depends on the seismic velocity and the density of the rock. So what kind of sound or vibration you're making and how fast it is, and the material you're trying to penetrate through. So anytime we have seismic waves that are reflected at junctions where there's a density or a change in the rock, we call that acoustic impedance. It's essentially the product of seismic velocity and rock density together. And the result you get then is this printout scale that does not show thickness of the units. It's showing the travel time of the waves, whether they slow down or speed up. To look at just the basic principles of seismic methods, this probably goes back to some very basic intro geology courses, but we have two main kinds of seismic waves. We have our P waves, which are compressional, and our S waves, which are shear waves. I like to think of a P wave as a punch and an S wave as a slap. It's a punch or a compression is forward propagating with the wave motion parallel to the direction of force. A shear wave or an S wave is more like a slap because it's a forward propagating wave due to perpendicular motion, kind of a sinusoidal back and forth. So our P waves actually are very fast. They're the fastest seismic wave, and they're also primary. They're the first ones that show up. Our S waves, which transverse, they're secondary. So if you imagine taking a slinky and you stretch it out and then let it go and it snaps back to its original form, that is how P waves move. That's how the particle motion is happening with a P wave. If you think about somebody cracking a bullwhip, that up and down motion that then moves forward, that's how particles move with our S waves. As you can imagine, a P wave can move through rock very, very, not to say easily, but it moves through because it's a forward propagating, parallel to the direction of force, wave motion, while your shear waves can get lost when they go through water or rocks of different densities. I should point out that when waves are propagating through sedimentary units, it's not always a matter of stop or go. We can also have reflection, which is one of the most important things. This is really what we're looking for, and refraction. So with reflection, the wave is going to meet that unit or that boundary, whatever angle it hits at, it then bounces off and returns at the same angle. And then we can calculate the travel time from that. That's what we're looking for. Good reflections give us good information. Refraction, though, is when that wave propagates through, it actually goes through the boundary between these different mediums, and it changes direction, it bends. So this does happen, and this is something that's going to produce quite a lot of noise, but we look at where we lose signal and where signal is returned, and that can result then in having more data that we can work with. And a few other warnings about seismic methods. Again, and I can't stress this enough, that you're not looking at readouts of rock layers like you would in a traditional cross section. It's very misleading because seismic models look a lot like rock units, especially when you're looking at very finely bedded units, but that's not what you are actually seeing. You're looking at seismic reflections, and they don't represent thickness. And there's a lot of things that can influence your data as well, what we call acoustic contrast, so how well the signal is showing up, signal attenuation or the reduction of a signal, any other interference, fluids that might be in the rock, all of these other things. So corrections are usually needed. You can't just do your seismic setup, send a shot through the ground, and the data you get back are perfect right away. You have to correct for a lot of these factors. So there's things we call static corrections, and these are going to normalize the signal of any of the data that we get. These will help to overcome elevation at the source of the receiver below the zone. So we have to make sure, if we're not, your ground isn't perfectly level, it has to correct for that. There can be variations in the velocity and thickness, especially in weathered zones. Weathered zones of rock are going to transmit and absorb signal much different. And the water depth, if you're doing something in a marine setting, how deep is the water and what's that sub-bottom velocity being impacted. There's also what we call dynamic corrections. These are going to correct for offset in the distance between that source, the receiver, the angle of the bed, again, if your units aren't perfectly horizontal. What we call deconvolution is reducing noise and distortion that might happen from environmental factors. And what we also call horizontal stacking, which is you're taking those primary reflectors and you're enhancing them so you can see them much more clearly. So there's a lot of corrections. Just think of it kind of like if you were to take an image with a digital camera and you're playing with it in Photoshop. You're not completely making something brand new, but you're enhancing things so details can be more obvious, especially for an analysis. So here's an example of another seismic method correction known as migration, which moves reflectors to where they should be. Occasionally your signal will drift or it will migrate. And again, that has to do with changes in the bed angle. It has to do with changes in the depth of the units that you're shooting, essentially. So in figure A of 6.9, this is before migration. There's not a lot you can do with that. But once you apply migration corrections, you see figure B, and yeah, you can actually start to see lines and packages that you can make some useful interpretations out of a lot easier. And finally, just like what you're doing with lab project number 2 in class, where you are describing lithology of a core and then making comparisons to well-logged data, we can make those comparisons again with actual either well-logged data or data from cores themselves and our seismic sections. They need to be calibrated. So in this case, we've taken a seismic section and we have stretched it and corrected it to actually show how it lines up with depth. So if you look very carefully on this image, on the left you see seconds, and then going down on the right side you can actually see meters below the surface, where we have late Paleozoic throughout Mesozoic units, most of the Mesozoic units. And you can see how we are going to have to correlate these. And once again, these reflectors are telling you where there's a difference in density. It doesn't necessarily say anything about porosity or permeability or lithology. With that, you do actually have to look at real rocks or, at the very least, well-logged data. Most of the types of correlations that we are probably more used to from our introductory courses are looking at lithologic similarity, where you're actually looking at outcrops and actual rock samples and tracing them from one location to another, either in making fence diagrams or large-scale cross sections. In this example, we're looking at an Upper Devonian section from Montana, and you can see how we can link across different types of units, units A, B, and C, based predominantly on lithologic similarity. Again, this requires actually looking at rocks. So you can either look at it in an outcrop or kind of make your own mini outcrop by doing a borehole where you can collect chips or actual core samples themselves. And as you know from the project you're working on, this requires going through things very, very carefully and having a systematic approach to describing the entire unit. And once we have a core, we can also collect wireline log data. These should be some things that you're a little bit more familiar with since you've been working on this in the project. Spontaneous potential, resistivity, and gamma. Spontaneous potential is looking mostly at distinguishing sandstones and shales, and this is based on the porosity of the material, so that's where we get spontaneous potential from. Resistivity is looking at the resistance to electrical current, and then gamma, of course, is looking at gamma ray flux as clays, predominantly potassium, uranium, thorium, clay minerals that have these elements in them, start to break down. So when we look at figures 12 and 13, figures 612 and 613, you can start to see some of the differences between these three. So here at figure 12, these are looking at spontaneous potential and resistivity logs as you look down a borehole. Notice that going from 0 to a more positive side with spontaneous potential, our shales are relatively low. We start seeing an increase in both cases with a sand. Notice that a carbonate unit goes really, really far. So our carbonates are going to show greater resistivity, but not spontaneous potential. I want to point that out, that if you look at spontaneous potential and resistivity and you go down from the top to the very first carbonate unit, so 4 units down, you barely see a blip on spontaneous potential, but you do see quite a lot with resistivity. So resistivity is really good at differentiating sands, shales, and carbonates. With spontaneous potential, it's more sands from kind of everything else. When we look at gamma, though, in figure 613, this is showing gamma from a Permian sandstone, actually, that was collected in 1982. And you can see that there is a slight difference. There's a bit of a gradient as we go from bedded sandstones to massive sandstones. So you can get a little bit of information from there, but not really that much. Gamma is, again, very good for differentiating clays from sands. But between these 3 types of curves, these 3 types of logs, you can get a fairly decent idea of what's going on in your subsurface. I also want to point out that with resistivity, because again, we're dealing with electrical current, you can start to see a difference in your spikes based on freshwater or saltwater penetration. If you look down at the very last sandstone unit in figure 612 towards the bottom and look at the resistivity side versus the spontaneous potential side, spontaneous potential for that entire sandstone mass is pretty much the same. But if you look at resistivity, there's a greater spike, not carbonate great, but greater spike with fresh water than salt water. And since these curves really help you differentiate our 3 main kinds of sedimentary textures with shales, carbonates, and sandstones, you can do exactly what you're doing right now in lab. You can start with describing a physical core. In this case, we're looking at the Simpson group. And then from there, you can correlate to resistivity and spontaneous potential logs across an entire area. So this is a little different than what you're doing. You're comparing how you can do it in one giant core, but you could do this with others. You can describe one core and look at what its logs look like, as you've already done. And then you could look at logs of a number of other areas and actually make a block model or a fence diagram of the entire region. So we can use this information together along with lithologic similarities from actual hand samples to get quite a lot of information. I want to switch gears a little bit as we look at section 6.2. We look at more lateral changes, and I want to introduce formally the concept of the facies, the sedimentary facies. Simply put, this is an assemblage of any rock, mineral, or fossil with features that reflect a depositional environment. So the classic example I like to use is a beach. If you go to a beach, everybody, think back to like your childhood vision of a beach. There's sand and there's shells, and there might be some sand dunes towards the back. That is a beach facies. Now, it can be specifically, you could describe what type of sand grains, the composition, so the chemical attributes. You could look at the biological attributes of what kinds of fossils you find associated, what kinds of shells, and what kinds of textures and fabrics you see. How are the sand bodies piled up on top of each other? What are their lateral and extents and their thicknesses? All of this goes into the facies. It's physical, chemical, and biological attributes that represent a depositional environment, key here, at a moment in time. Because facies do change, and facies change is one of the most important aspects of reconstructing depositional environments in stratigraphy. You have to look at the lateral variation in all of these physical, biological, and chemical characteristics from one deposit to the next, and you'll see that, once again, environments change. So as you go back to our beach example, at some point, if you go swimming out in the water, you're going to come across barrier islands or lagoons or coral reefs, and there's no abrupt sudden wall separating these out. They are lateral gradations from one environment to the other, with these physical, chemical, and biological attributes gradually changing as well. And they do this laterally at any given time. So right now, as you are listening to this lecture, there is sand being deposited on a beach in Florida. There are clays being deposited in Lake Winnebago. There are tills being deposited up in Labrador, up in Canada, as the ice sheet continues to melt. All of these things are happening contemporaneously. They're all happening right now. And in between them all is a number of other depositional environments that all grade in and out of each other. So these are all happening concurrently in this snapshot in time. So facies will shift and blend from one to the other. And that's an important part to remember as we go into discussions of Walter's law. Talk a little bit about how our facies change and how we identify them based on lithology, because we have biofacies and lithofacies. I want to start with lithofacies. This diagram, figure 619, we have A and B, and I've added some notes here in the middle between them. I put T1, 2, and 3, and those because these bold lines in both A and B represent timelines. So timeline 1, everything below that was deposited at one time, and then between 1 and 2 is another depositional event, and then 2 and 3 another depositional event, and so on. If we look at the facies we see in figure A under time 1, you'll notice that we have a carbonate that blends into a shale, that blends into a sand, and it does this in time 1, 2, 3, and onward. Okay. In other words, in this case, we're seeing constant boundaries between our lithofacies as that sediment accumulates. In order to get this, you would have to have, from time 1, 2, 3, and onward, you would have to have absolutely consistent water depth. So the water depth couldn't change in relation to the sedimentation rate, which could not change. The sediment composition would have to be the same. The subsidence rate of the crust as it's being loaded with sediment would have to be consistent. This is virtually impossible. What you're seeing in 619A, you will probably not see in nature. But let's look at B. In this case, our facies boundaries do shift. Notice that if you go from time 1 all the way towards the top, our facies are shifting over towards the left, and that's because we're seeing clastic sediment supplied to the right. This would account for water depth variability and maybe a decrease in the crust subsiding. But again, parallel timelines suggest, and being totally equal in thickness, suggest that sedimentation rate is absolutely consistent. This is possible, but very, very unlikely, because your sedimentation rate is almost never consistent for any considerable period of time. So what does a series of facies over time look like? More like this usually, but again, on a much, much larger scale. In this case, we have differential sedimentation rates, and you can see that because our timelines diverge. Notice we still have 4 bold lines there. Those are our timelines, and they split apart and get thicker as the sediment accumulates, because in some places you're going to accumulate more, or the crust is going to subside more, other places less. Water depth is going to vary. Types of sediments going to vary. This is more common with what we see. Here's an example. If we look at the restored cross-section of the Catskill Delta from the Devonian of New York, you can see we've kind of drawn in our timelines, and they vary in thickness from one side to the other. They vary in thickness in between each other. And notice also that our facies are blending from one kind to another I don't want to say inconsistently, but each timeline is kind of doing its own thing. And that's because during that time, there were a set of unique characteristics. So, when we draw diagrams for classes and things, we try, things get simplified sometimes into parallel, perfectly, equal thickness rocks. In reality, it's much more variable, and that's an important thing to keep note of. Finally, now we can look at Walter's law, because that Catskill delta figure actually shows Walter's law. And Walter's law states that in a continuous vertical sequence, the succession of vertically deposited units reflects the original contemporary lateral arrangement of facies in the area. So for example, figure 622. During a transgression, which we'll get into in a moment, you'll notice that we have, in a sedimentary sequence, we have sand and then shale and then carbonates. Okay. Each one of these facies represents a different time. However, from that we can interpret that in the past, at any moment in time, this is still the lateral orientation of those units. So we look down in between our transgression and regression columns in this figure, and you see water depth with your sands, your shales, and your carbonates being deposited in progressively deeper water. So the sands are in the most shallow, then the shales, then the carbonates. That pattern, that arrangement of sand, shale, carbonate, is reflected in both the transgression and regression, just the order is reversed. But if we were to draw in timelines and have repeating sequences, in this case, the sand of the regression is going to be from time 1, which is displayed. The shale would be from a second time 2, and then the carbonates from a time 3. The regression would be the opposite. The carbonates would be from time 1, the shale from 2, and the sand from 3. So we have difference in lateral and vertical changes due to Walter's law. Okay, so this is how a geologist can look at a sequence of rocks, a stack of rocks that may span hundreds of millions of years, and reconstruct the lateral distributions of environments at any given moment in time represented by that column. So let's talk about transgressions a little bit more. A transgression is a sequence of rock that shows the geometric relationship of graded to shore parallel facies belts. These are going to have fining upward sequences. You're going to have your near shore units overlain by offshore units. Okay, so what's happening here is the shoreline is migrating landward. You are seeing a basinward facies overlie landward facies. Okay, so here we also see Walter's law demonstrated here. We have our beach, our near shelf, and our far shelf units at a snapshot in time. But over time, as that shoreline migrates landward, on top of that sand, you'll deposit another shale, and on top of that shale, you'll deposit another series of carbonates. So it's a landward movement of the shoreline as we go progressively deeper. It's a progressive deepening. So you stand on the beach, and over millions of years or hundreds of thousands of years, you would be under more water as that shoreline moved past you and beyond you. Regression is the opposite, a graded shore parallel facies belts, where there is a coarsening upward sequence. Because in this case, our landward facies overlie basinward facies. We are seeing a basinward or seaward migration of the shoreline. So a progressive shallowing. You may start out in ankle-deep water, and millions of years later, you are quite some distance away from the shore itself, and you're on dry land. So the shallowing upwards, we see shoreline moving basinward through time. And again, Walter's law is demonstrated. We go sand, shale, limestone. We still see sand, shale, and limestone, but just the order is the opposite of what we saw in our transgression. Now, regressions can be a little bit more complicated, though. Because with regressions, the shoreline may be moving seaward, but this can happen in a couple of different ways. So with a regression, all we can really say is that the shoreline is moving seaward. This could be a sea level drop. This could actually be a eustatic sea level drop, where we're pulling water out of the oceans and maybe storing it as glacial ice, thus lowering the amount of water in the basin. Or it could have nothing to do with eustatic sea level. It could entirely be from an increase in tectonic uplift, which is draining your shoreline. Or it could be a huge increase in sediment supply into a basin that otherwise isn't changing parameters. Like you totally fill up a basin, and pretty soon you change the way that it's accumulating sediment. Or you could expand the size of your basin. So one way that we can form a regression is called progradation. And this happens by having an excessive sediment supply relative to the basin size, or what we call accommodation space. So this is a figure from a different source, not from your textbook, but you will have a copy of it. And in figure A, or part time 1, you can see we have a sea level. You can see there's a beach, and then it grades into a shale. During time 2, we have added more sediment to that basin, and now the land is kind of prograding outward. And then 3, and then 4, you can see how it continues. We still have that vertical profile of coarsening upward. It's still a regression, but this has nothing to do with raising and lowering sea level. Notice the sea level is absolutely consistent throughout all 4. This does happen. This is as you kind of choke your basin with more and more sediment without changing its parameters. So progradation is a common way of getting a regression. Now, if we're getting an excess sediment supply, where's that sediment coming from? We'll be talking about that in upcoming weeks, but that's something to kind of start thinking about now as we think about cycles that we can see in sedimentology and stratigraphy. We also have a type of regression that's called a forced regression. Now, in this case, we do see a relative sea level drop and the formation of an erosional surface. So these have unconformities. You are actually dropping sea level in this case, and you're subaerially exposing units. These can be recognized in your stratigraphic columns. You'll see a coarsening upward sequence indicative of a regression, but you'll start seeing paleosols, so kaolinitized clay-rich soils. There could be disconformities or some kind of angular discordance from units. You'll see plant remains in rooted zones if it's been subaerially exposed in the latter part of the Paleozoic or onward. You'll see these basinward shifts in sedimentary strata, what we call a non-genetic stratal relationship, which means instead of it being a nice gradual change of coarsening upward, it's very abrupt. And most importantly, these strata do not work in accordance with Walter's law because sometimes we skip units. So this might be hard to mentally visualize, so let's look at some examples of a difference between a progradational regression and a forced sea level drop regression. Okay, so on the left you have your progradational schematic of a prograding regression, and on the right you have a schematic of a forced regression. So we're looking from the top of these to the bottom. Okay, so during time 1, you'll notice with our forced regression and our progradation, we have coastal plain, then we have our foreshore, upper shore face, lower shore face, and then our deep water offshore deposits. With a progradation, you're just keep adding the same facies belt, but it's shifting outward. It's going outboard, so to speak, because we're just adding more sediment. We have this huge supply of sediment causing the basin to begin to fill, and it just starts piling up the same way it did before. And notice going from time 1, 2, and 3, looking entirely at the regression schematic, the progradation schematic, you can see that we still end up with coarsening upward sequences. It shallows upward, and we have Walter's law represented. However, if we look carefully at our forced regression schematic, and I know these images are kind of small, so I'll include blown up versions on Canvas. With the forced regression, you start with that same situation, coastal plain, foreshore, lower shore face, offshore, and then you have a lowering or a falling of actual relative sea level, and then you start depositing outward. So notice we've shifted everything way out to sea, much more sidestepped than we did with the progradation. And as a result, we're going to start eroding some of the previously deposited units, and you can see that down at the bottom where there's been erosion. We don't see that with progradation. Progradation is just building outward. Forced regression is forcing that sea level down, or the sea level is down, and it forces a lot of these units to erode and remobilize those sediments out to sea further. So again, these can also be identified as very distinct units. So when you're looking at a stratigraphic column, you can recognize a finding upward sequence as your transgression. But when you start to see the regression, is it a forced regression or a progradation? With a progradation, it's still going to follow Walter's law. With a forced regression, it won't. So what drives transgressions and regressions? Well, you can't always tell just from looking, because a lot of things can play into these. You can look at your relative sea level change, which could be local. You can have eustatic sea level change, which could be global. And it could be sediment supply, which can drive transgressions and regressions, but it has nothing to do with relative sea level. It's not going to be eustatic or isostatic. It has to do with sediment source and sediment supply. And as we'll get into a little bit in the next few slides and also in the next couple of weeks, it also depends on when in time, in geologic time, that's happening. All you know when you look at a transgression and regression is that the shoreline has shifted. There's a lot of different factors that can play into what's causing that sea level change, and that requires looking at something a little bit more broad than just a transgression and regression. So these are very important to note, but they always require further exploration. If a lithofacies is the geological physical characteristics of a facies based in sedimentology and lithology, biofacies is based on fossil content. So this is specifically looking at the aspect of a facies that is made up of its biological component. And we're not really going to look at rock type. Even though that does play into it as we start to combine litho and biofacies, we can make some really interesting interpretations. But first, we can use biofacies as a way of inferring paleochemical settings that otherwise might not be preserved in the lithofacies. For example, turbidity, salinity, oxygen content. You can't always tell that just from looking at a sedimentary rock. You can interpret environments, but you can't always interpret environmental conditions. You can, though, with biofacies. So if we're looking at, let's say, a package of rock, and we notice that we have a lot of sponges and blue-green algae and maybe some, I don't know, bivalves. Okay, looking at how many we have, we can start to make some ideas. Are we looking at a normal marine environment or traditional brackish or full brackish? Is it hypersaline? We can start getting these ideas depending on where we find these organisms today. We do have to be a little bit cautious because we don't want to apply too much onto the way modern organisms behave compared to fossil organisms. We have to be cautious with that and understand evolution. But we can use organisms today and look at what kind of environments they live in and make some paleochemical inferences from that into our biofacies. So again, we have to be careful because if we consider like modern or extant brachiopods, mostly are attached, and a lot of our extinct brachiopods were a little bit more free living or had the ability to be. So we have to understand that once an organism is found in a place doesn't mean it necessarily lived there its entire life. But here we can see some different biofacies along open sea, different parts of the shore face, upper, middle, and lower, and what kind of organisms, whether it's trace fossils or actual invertebrates, that might tell us something about what type of environment and its conditions that we're living in. Together, biofacies and lithofacies can produce some pretty detailed environmental analysis. And let's look at an example of how this can happen. So we can actually infer some hydrographic conditions from, we're going to go back to looking at some of those deltaic Devonian units, in this case the Sonia group. And there are two deltaic units in the, we're looking just at the lithofacies here, at the bottom, that are separated by black shales. So let me point those out to you real quick. Talking about this right here, that black shale. So we have a lower lithofacies and an upper lithofacies. And notice that they are quite different. Below that black shale, we have a gray shale or a silty shale, and then we start getting into more of a silty shale, but on the upper portion, it's a lot more sandy. And we actually start getting into some shoreline sandstones as well in the upper facies. Now, if you look in that lower delta deposit, again, sandy shales, pro-delta, delta front type environment. However, the biofacies corresponding immediately above, which is predominantly made of brachiopods like Protectida and Bellerophon mollusks, don't correspond with the lithofacies. Notice where our Protectella and our Bellerophon biofacies are compared to the differences in the lithology. So our lithologic changes predominantly in this lower facies are over here, and here's the separation between our biofacies. They're not lined up very well. That's kind of strange. That means we're finding Protectella here and only the Bellerophon here. So why is Bellerophon only up in this area? And it's in the same rock type. Bellerophon communities, those types of mollusks, are actually what we call saline tolerant. So they don't live in high saline environments. They live in low salinity environments. The biofacies boundary, in this case, why do we have a difference between where we find Bellerophon and where we find Protectella communities, is probably controlled by salinity. So we're starting to get into slightly less salinity as we go towards the Bellerophon. The Protectella is probably a little bit better at handling those types of conditions. You're not going to see that just looking at the rock, but you do see it when you look at the biofacies within that rock. So that tells us that that specific spot, as we're accumulating the same kind of rock, there are some chemical differences. Now let's look at the upper unit. The upper delta, we have sandy kind of barrier bar units, some reworked barrier lagoon complex. This is where we're going to do our shoreline sandstones, much more sands and silty shales. The biofacies here, Rhipidomela and Cypricardella communities, do correspond really well with our changes in lithofacies. So where you get one community is in one rock type and you get a different community in the other rock type. So in this case, both the biofacies and the lithofacies are going to be controlled by the same physical characteristics of that environment. So this is just an example, and by the way, these are being plotted against time, not thickness, but this shows a really good example of how you can use these together to learn something that by themselves they wouldn't tell you. Without knowing the sedimentological context of those fossil communities, we wouldn't understand the chemical conditions and vice versa. You need both of them to make these types of interpretations. And so figure 6.26 kind of shows some reconstructions of these two deltas that we just discussed in the Sonia group. Part A, this is what we saw with our first, the lowermost delta deposit, where you have a chemical difference between low salinity and normal salinity wedge, and this is where we're getting our different biofacies. And then in our second example, our Nile or Mississippi type barrier lagoon and mixed with near normal salinity throughout, which is why we saw distinct differences in our biofacies that corresponded with the same distinct differences in our lithofacies. So again, by combining these two types of facies analysis, biofacies and lithofacies, we can learn a lot more about the environments that we're looking at. And finally, I want to finish up the lecture for this week by looking at just some very basic philosophies about mapping. Mapping is always going to be extrapolated based on what you can see, so very limited exposures. And this goes back to even some stuff you've probably done in some intro courses where you're given a partial outcrop and some other data from the area and you have to fill in the map. So whether we're looking at figure 6.27 like this one where we have isopac information and we have lithology, and if you've got certain types of current indicators, you can get current directions and of course biofacies in there as well. You can make some educated guesses about what the region may have looked like by filling in the rest. Now, the cool thing about this is if you can go out and collect more samples, you can always either confirm or refute your analysis with additional data. And that really is the main point of this, is that really the detail is dependent on the variability of data. If we look at 6.29, such as here, you can see that we have this aeronautical chart of the this Mississippi River Delta. Now, if we do 12 random points of observation, we see a few areas where there's land and a few areas where there's sea. If we add 25 random points, we see what looks like an island offshore of this main body of land. With 60 random points, we actually see that it's more of a distributary. With 169, we can actually start to distinctly point out where we have fresh water versus land versus sea. And then when we get to 300 random points, you can start calling out a little bit more. You can start seeing barrier islands and other things. So this is just an example of how with more data, more detail is obvious, which is pretty obvious in and of itself. But when it comes to mapping, the more data you can get, the more detailed your map is going to be. So that's an important thing when we're starting to go through the next couple of projects that we'll be doing in lab as well. And so that concludes the lecture content for the week. Next week, we'll be looking at Chapter 7 of the Brookfield text, which is the time dimension. We'll be focusing quite a lot on biostratigraphy and its related methods. Just a couple of quick reminders that Project 2 is due on March 5th, and Project 3 will be assigned on March 5th, and it will be then due on March 19th. So I look forward to seeing everybody in lab.